Hello. We've been working for quite some time on this projectile motion cannon simulation. As you know, we can do all sorts of things to this cannon, which creates a variety of different functions. So we could have height as a function of initial speed. We could have height as a function of the angle launched. We could have horizontal distance as a function of the angle launched, horizontal distance as a function of the height of the cannon, etc., etc. So we've been working with this for some time. So let me summarize what we should have learned so far. What we should have learned so far is that, not what we should have done so far, is first we were learning how to write function statements. So these are descriptions of functions. We have the height, in this case, is a function of the initial speed. In addition, I put down a couple of details for my simulation so I could recreate it, and I fixed the angle at 90 degrees, and the height of the cannon was at ground level. So these are some things that I have to make sure I keep the same next time I go back to the simulation. Now, what I did was I chose to keep the thing at 90, and I kept messing around with the velocities, changing them and seeing how that affects, and then I measured. And when I did that, I was able to collect the data shown here. So this is from a while ago. We all collected the data. Then we learned that these values are just specific points in time. If we were to plot the data on a graph, we would start to recognize a trend. And what I see on this trend is there's not a constant rate of increase in the height that's being launched here. As a matter of fact, as I increase the velocity, it has a sort of an ever-increasing effect on the maximum height achieved. So this is not linear. In fact, it seems like if I were to go to 40, I could probably expect a distance somewhere here in the hundreds for my height. So that's where we started days and days ago. Now we are able to utilize technology. With the technology, what I was able to do was take my data, and if you remember, what I did is I did the old right-click copy and went over to a spreadsheet and pasted it, and then you copy again. So you right-click copy, and we go to this, which was the Desmos link that I sent you guys. So on this Desmos link, I pasted in the data table, and I chose from a list of 3 different functions which one fit the data as best as possible. So I got a really good fit here, and I ended up with this format. This is called a quadratic function, and the a value is here. This b can be substituted by this b number, and this c can be substituted by that c number right there. So what I've done is I've used technology to create an equation. So here's what I'm actually going to do. I'm going to write down, oops, that didn't work well. Let's undo that, and undo this, and undo, there we go. So I write down the equation in its entirety. If you want to make an exponent, by the way, all you have to do is highlight, so I can make 7 an exponent by highlighting it. And then you go to Format, Superscript. So now that is 7th power instead of 7. I'm going to undo that, of course. There's also an equation editor, but if all you're going to deal with is an exponent, you don't have to worry about that. Just use superscript. So anyway, I write down the equation. And my next step is to see what this equation is good for. What the equation enables me to do is to find any maximum height for any velocity I want. So this is telling me that if I shot at 7.4 meters per second, that the cannonball will go 2.82 meters maximum. Extended out here, if I shot the cannonball at 39 meters per second or so, I would end up with about 78 meters up in the air for that particular cannonball. So what I did is I picked something that was not from my given data because I want to find something that I haven't actually experimentally discovered yet. So here's what I did. I chose randomly an interesting number like 38.2, something that I wouldn't have guessed and I wouldn't have collected myself, just a weird number. So I threw in 38.2 as the initial velocity, and my equation told me 75.31 will be the maximum height. So that being said, I now had to interpret this point in English. So I said, h of 38.2 equals 75.31 means that if the cannon was fired with an initial velocity of 38.2 meters per second, that should say, then per second, then the cannonball would reach a maximum height of 75.31 meters. So this is an interpretation of what should happen, and it's based off of what I learned from looking at my graph, 38.2 and so on. Now, in order for this to have any real benefit, I want to know how accurate is my equation for predicting what's going to happen. So what I did is I went back to my simulation and I set up the 38.2. 38.2 was the velocity that I was curious about, and I kept the angle the same, and I kept the cannon on the ground, and here's what I did. I measured 75.3, which is approximately what my equation said I should have. So I extended the tape measure up until I reached the correct height, and then I hit fire, and I watched as the cannon went all the way up to exactly the top of the tape measure and then fall back down again. So what this says, well, I didn't say score, but I talked about it down here. It says when I ran the simulation, the blue marks took me all the way up to the target without actually reaching it. It's close enough for my liking to be effective. So once again, you're going to repeat that for the second function. We have the data table, we have the graph that we made by hand, and we also have now the new work that we did with Desmos. The Desmos put in an equation that's going to model the data as best as possible. So I write that equation here in the document, then I extrapolate. That is, I find another point somewhere on the graph, and this has to be edited as well. I found the point 20, 21.49. I had to use 20 because I found out the simulation only lets the cannon go 20 meters in the air. Can't go any higher than that. So I maxed that out to find out where I'm going to end up. And according to my equation on Desmos, and here it is right here, when x equals 20 meters, we can expect that the y value, which is the horizontal distance, is going to be 21.5. So that's what I translated right here. This is my translation of what this means, which is this point on the graph. And when I go down and actually set it up, first of all, I had the height set up at 20 meters. From that spot across, I went 20.5. I put down the target, I hit fire, and then boom, I got a core. And if I moved the cannon, I would see the S. But I guess we'll just call this a core. But it's not common, don't worry. All right. So hopefully this has helped you understand what your document should look like. I want to say one last thing before I close this video, and that is I have to look at a lot of these. It would be really nice if we all follow the same format. So notice again, we have description, we have any sort of part of the description goes here. Then we're going to have a data table. We're going to have a graph that we made by hand, graph made by technology, the equation that was made by technology, an extrapolation or interpolation, and a reenactment of the experiment to see that it works. Hopefully you'll understand why we're doing this. You can see how we can go from a simulation to a table to a graph to an equation to predictions into the future. Because of the work I did with function equations, which are all collected data, I'm able to predict the future without even having to do the experiment anymore. So do that, and I'll be a happy guy, and so will you. Have a good day.